Hi everyone. In this video, we'll discuss a special type of continuity called uniform continuity and explore the relationship between uniform continuity and the previous definitions of continuity we've looked at. So we want to begin today by defining what we mean by uniform continuity, or what we mean for a function to be uniformly continuous. So we say that a function f is uniformly continuous on E, where E is a subset of the domain of f, if and only if, for every epsilon greater than 0, there is a delta greater than 0, such that whenever x1 and x2 are in the set E, and the distance between x1 and x2 is less than delta, then the distance between f of x1 and f of x2 must be less than epsilon. So let's first examine this definition and think about how it differs from our usual definition of continuity. Now, the first thing we note is that we're defining here what it means for a function f to be uniformly continuous on a set. If you think back to regular continuity, we first defined continuity at a point, and then we said, well, a function is continuous on some set if it's continuous at every point in that set. So the first thing to note is that this definition for uniform continuity only works for a function on some set, right? So you can have a function that is uniformly continuous on a set. There's no notion of uniform continuity at a point. The other things, as we start to go through here, that we'll notice, again, and a lot of this stems from this fact that uniform continuity is a property of a function on a set versus at a point. The other thing we notice, so a lot of this sort of reads the same. So if for every epsilon there exists a delta such that, now before, because we would have been defining continuity at a point, we would just here have said whenever x is in E, or whenever x is in the domain of f, if we were looking at the whole domain. So whenever x is in E and x minus a is less than delta, then f of x minus f of a is less than epsilon. So in sort of our regular definition, right here, we would have like an x minus a is less than delta. And here we would have something like f of x minus f of a is less than delta. And anytime you were talking about, sorry, is less than epsilon. And anytime you were talking about continuity before, again, this a was fixed. You were talking about continuity at a particular point. The fundamental difference here in this definition is that you are saying that for every epsilon, you need to be able to pick a delta that works for any 2 points. Okay? Before, you were trying for every epsilon to pick a delta that for some a that had previously been fixed, whenever your x was within delta of a, then f of x minus f of a would be within epsilon of each other. But now you're saying for every epsilon, you need to be able to pick a delta such that if you take any 2 x values in this set, x1 and x2, as long as those x1 and x2 are close enough to each other, as long as they're within delta of each other, then the absolute value of f of x1 minus f of x2, their outputs, the difference in their outputs ought to be within epsilon of each other. To help sort of make sense of this distinction, I've got a little visual here. So let's sort of contrast what it might look like for a function that is not uniformly continuous. It is continuous, but not uniformly continuous, versus a function that is uniformly continuous. So again, the main idea here is that for a function that is uniformly continuous, I need to pick a delta that only depends on epsilon and not on the specific point that I'm looking at in terms of continuity. For a function that is not uniformly continuous, my delta is going to change as I change the point that I'm looking at continuity about. So imagine you have an epsilon, it's been fixed. Okay, so that epsilon tells you what you want the limit of the difference of your output values to be, right? So here these are sort of represented by heights of these little boxes. Okay, and same thing over here, right? Heights of these little boxes you can sort of imagine are all epsilons. And the question is, can I find a delta so that whenever my x values are within delta of some particular a value, my f of x minus f of a will be less than epsilon. So over here, for example, you can see, okay, like there's a delta, right? If my my x values are in this range, then you can see all of my function values are within epsilon of f of a, right? They're all sort of in this little epsilon box. Same thing up here, but notice as you move on this graph, because of the way the function is sloped, your deltas are actually going to become smaller and smaller and smaller and smaller, right? So as you keep the same epsilon, but as you move your point, your delta values are changing. And in fact, your delta values, you can sort of imagine as you go this way, they're actually sort of squeezing down to zero, right? On the other hand, over here, notice that over here, I could just pick one particular delta value. And no matter where I am on my function, as long as my two x values are within delta of one another, then my function outputs are always within epsilon of one another. Another way to say that is essentially I can use the same delta at every point over here. Okay. Now, that's not to say the optimal sort of maximal choice of delta could change from point to point, but I can pick one value of delta that's sort of like the smallest delta necessary to make sure it works at every point, right? Over here, I can't pick a smallest delta because my deltas are getting smaller and smaller and smaller as I move towards this asymptote over here. So again, the main idea is essentially that for regular continuity, my delta is allowed to change as I move amongst different points in my set where it's continuous. For uniform continuity, I want to be able to pick one delta that works for every point in the domain or in the set that I'm examining continuity on. Okay. All right. So let's start by looking at this for some particular examples. Let's start with something, you know, so we're going to start with a continuous function, right? We already sort of get the idea probably, right? Uniform continuity is a stronger form of continuity. So every function that's uniformly continuous is also continuous, but not every function that's continuous is uniformly continuous, right? So uniform continuity is a stronger condition, right? If you're uniformly continuous, you're definitely going to be continuous, but not every continuous function is necessarily uniformly continuous. So let's start with a continuous function, and let's look at this function on this set. So let's say that our goal was to show that this was uniformly continuous, right? So again, this is a property of a function on a set, so we need both a function and a set. So f of x is equal to x squared on the interval 0, 1. So if I was going to claim here that f is uniformly continuous on this set E, okay, then how would I do that? Okay, so what do I need to do? Well, I need to show that for every epsilon there exists a delta, so I'm going to take an arbitrary epsilon greater than 0. So take an epsilon greater than 0. Now I need to describe how I'm going to choose my delta here. So I'm going to need to choose delta equal to something as we sort of done before. I'm just going to leave that there for a second. Hopefully I'll figure out what that needs to be and come back to it. So choose delta equal to something such that whenever x1 and x2 are in my set E, so in this case, my set E is 0, 1, the closed interval 0, 1, and x1 minus x2 is less than delta. We have, okay, now I need to look at my output values. So if I look at f of x1 minus f of x2, well, let's see, what is that? That's just going to be x1 squared minus x2 squared. All right. And now as I get here, I look and say, okay, somehow I need to use this condition about absolute value of x1 minus x2. It'd be nice if I could get an absolute value of x1 minus x2. And what I notice is that I can actually, this is a difference of two squares, so I can factor. This is x1 plus x2 times x1 minus x2. And now I know something about this quantity, right? It's strictly less than delta. So this is less than x1 plus x2 times delta. Okay. And now the one fact I haven't used so far is that I know that x1 and x2 are in the closed interval 0, 1. So I can look, using that information, I can look at this quantity and say, well, what's the biggest that could possibly be, right? So the largest, in the worst case scenario, x1 and x2 are both 1, and this thing is 2. In every other case, this value is less than 2. So this is going to be less than or equal to 2 delta. And that's where I remember, oh yeah, I want this to be less than epsilon at the end. So if I make my delta epsilon over 2, then this would just be 2 times epsilon over 2, which will be epsilon. And now what I've done is I have demonstrated, right, that for an arbitrary epsilon, if I just choose my delta to be epsilon over 2, then whenever x1 and x2 are in this interval and x1 minus x2 in absolute values is less than delta, then the difference between f of x1 and f of x2 in absolute values must be less than epsilon. Okay. So this is sort of a nice first run through. We've proven our claim, check. This function f of x is equal to x squared is uniformly continuous on this closed interval 0, 1. All right. Well, let's maybe try to modify this. Let's keep maybe sort of broadening the type of set we're looking at. A nice thing often to do is just try to, okay, it works for this. Now, what if I broaden it a little bit? And can I keep pushing it until I sort of break it, right? Because that will help me understand not only the cases in which this works, but also when this fails and what sort of issues I might be looking at there. So let's swap our example slightly. So you'll notice here now I've kept the same function, and now I'm working on a closed interval, but I'm going to work on a generic interval AB. Okay. So what I really want to do is just look at this same proof and go, well, what's special about 0 and 1? And could I modify this to just work on the closed interval AB? Okay. So I'm actually not even going to change, I'm not going to rewrite the whole proof. We'll just modify slightly. So I don't know if the same delta is going to work again. I might need to modify my delta. So let me take that out for now. Okay. I'm going to be on the interval AB. And let's see, I started using really particular things right here. Okay. So if I'm just sort of analyzing my proof, right, everything is good minus these things that I've taken out, right? Okay. So I'm going to assume I want to let epsilon greater than 0 be given. I want to choose a delta somehow, got to figure that out, such that whenever x1 and x2 are in, all right, the closed interval AB, and absolute value of x1 minus x2 is less than delta, we have, okay, this is just plugging in what f of x is. This is just doing some factoring. This is using the fact that absolute value of x1 minus x2 is less than delta, which is part of my definition. So great. All right. Now I get to this point. Okay. And it might be tempting here to say what? Well, the worst that x1 could be is the letter B, and the worst that x2 could be is B. Okay. But be careful. Well, be careful. No pun intended, but it's a pun nevertheless. So be careful because we have absolute values here, and we have to worry about sort of negative values. So like if my interval was, of course, if my interval was 1, 5, then I would just say, oh, the worst this could be is 10, right? But if my interval was -5 to 1, right? Now it's possible that this could be -10, right? So this could be -5, -5, in absolute values that would become 10. So I need to figure out sort of what's the largest of my A and B in terms of its magnitude. Okay. So this is where I'm going to have to actually add a bit to this proof. I'm going to come in here and I'm going to need to do this before I choose delta, and you'll see why in a second. But I'm just going to add a little sort of piece in here that says let capital M be equal to 2 times the maximum of absolute value of A and absolute value of B. Okay. Now, doing that, right, whichever of these is bigger, right, this will be less than or equal to 2 times whichever of these is bigger. So this will certainly be less than or equal to m. So now I can say this is less than or equal to m delta. And now I'm just going to choose delta, delta to be epsilon over m. And again, here I'm able to complete my proof, right, for a generic interval AB. So I notice that at least for this function x squared, right, I can show that it is uniformly continuous on any closed and bounded interval um, in the reals, right? Makes me start to wonder, right, if I could do this for any compact set, right? You sort of started thinking reals, if something works on a closed and bounded interval, it one of two things. Either I should be able to do it on any connected set or any compact set. Here I think it's probably compact. And let me explain my rationale there. Um, when you think about compact sets are really sets that are almost finite, right? They're not finite sets, right? There are uncountably, infinitely many things in here. It's far from finite, but it behaves like a finite set because you can cover it with a finite open cover. Every open cover has a finite subcover, right? So somehow, even though it's not a finite set, it sort of behaves like a finite set. And I sort of think, if I was looking at this function on only finitely many points, well, it would certainly be uniformly continuous, I would think. So it seems like probably this works for compact sets, right? Now that I'm seeing it, it works here, right? It's starting to clue me in that it might be compact sets. It's probably not connectedness. I'm not really using anything about ordering or anything that makes me think there might be some connectedness piece of this. So probably what is true is that this is true on compact sets. So we'll talk about that a little bit later. Um, but then I started wondering, can I push it? Maybe I can push it even further, right? In R, uh, by the Heine-Borel theorem, right? Compact is the same as closed and bounded. So could I forget the closed part and could I look at just the bounded part? Okay. Um, it actually turns out I can. So, and the proof is going to be fairly similar. So let epsilon greater than 0 be given. And okay, I probably am not, I don't have an interval anymore, so I can't do this, but I'm going to use some sort of bound. So I'm probably going to need this let m be something, and I'm going to need to choose a delta. And now it's just whenever x1 and x2 are in the set E. Remember, this is true. Okay, and then again, similarly, everything goes fine until this part, and we got to figure out what we might do. Okay. Um, well, what is what is this? Okay. So again, I'm assuming now that my set E is bounded and x1 and x2 are in E, that means that there is some upper bound on what x can be, and there's also some lower bound on what the x values can be in E. Okay, so what I'm going to do here, I'm going to do something a little bit different. So I'm going to let m be a real number such that since my set is bounded, I can choose a real number such that all my x values are between minus m and m. Okay. So now if I do that, when I come down here, well, the worst this could be is either minus 2m or plus 2m, but in absolute values, those are going to be the same. So this will be less than or equal to 2 capital M delta. And in this case, I will simply choose my delta to be epsilon over 2 to the capital M, which will still give me epsilon. So again, even in this bounded case, I don't actually even need the closed bit here. As long as my set is bounded, right, I can find, as long as my subset of my domain is bounded, I can show that this function is uniformly continuous. Now again, I'm just looking at one very nice function, right? So we don't want to draw too many conclusions from this, but that's pretty nice. Now I start to wonder, like, maybe this function is just uniformly continuous on every subset of the domain, right? So the last case I would look at is, well, what happens if I just look on all of R, right? Is this uniformly continuous on all of R? Okay. All right. So last example here. What if we wanted to look at this function on all of R? What would happen? So let's say, okay, I'd let epsilon greater than 0 be given. Maybe I would need some sort of condition, but I can't bound anything anymore. So I probably don't need this, right? R is unbounded. So if I'm going to make this work, it's not going to be by using a bound. Such that whenever x1 and x2, okay, now all I can say is that they're in R. And x1 minus x2 is less than delta. We have, okay, all this will work again until we get here. Yeah. And now this is where we really start to see the problem. If x1 and x2 are just in R, even if they're really close together, I can keep pushing them further and further out. So I can make this quantity arbitrarily large. So now consider this. Suppose that we had some delta that worked. Okay. So say that let's say epsilon is equal to 1. So let's even start in, let's say, consider epsilon is equal to 1. And let's just, for the sake of argument, we're going to suppose there exists a delta. And let's say all we know is that there's some delta greater than 0 that works. Okay, so let's just see, imagine that we had epsilon equal to 1 and suppose there exists a delta greater than 0 such that whenever this happens, then we still have all this, and this difference is less than epsilon. Well, you can immediately reach a contradiction because I can choose x1 and x2 large enough, right? If epsilon and delta are fixed, I can choose x1 and x2 large enough so that this times delta is greater than epsilon. So I can choose x1 plus x2 sufficiently large so that this x1 plus x2 times delta is greater than or equal to 1, right? I can always choose, this is actually a consequence of the Archimedean order property, right? I can choose some real number, right, such that this times delta will be bigger than 1, which is a contradiction. So what we've actually done here is sort of a mini proof by contradiction to show that here in this example, f is not uniformly continuous. Now, I haven't written this up as a super nice formal proof, but this hopefully sort of gives you some idea of why in this particular case, f is not uniformly continuous on this set E, which in this case, the set E is all of that we're looking at is all of R. Okay. So functions we can talk about functions being uniformly continuous on sets. Not only, obviously, as you change the function, whether or not it's uniformly continuous or not can change, but also as you change the set, right, this can change. And so again, we go back to this question, looking through these examples, we saw that at least on compact sets, It actually turned out here even a bounded set was fine. But in general, on a compact set, things seem to be working fairly well. And so we might sort of wonder if there's some relationship between, like, obviously, if I'm going to have a function be uniformly continuous, it's got to be continuous. If it's continuous on a compact set, it seems like maybe it might just also be uniformly continuous. And so that's the next thing we sort of want to address is what relationship is, if any, is there between uniform continuity, and compact sets. So if we look in the book at theorem 2.22, it helps answer this question. The theorem in the book says if f is continuous on the closed interval AB, then f is uniformly continuous on the closed interval AB. Now, what I'm going to do is I'm going to show you a proof of this. Okay, we're going to prove the statement as it's presented in the book. But then we're going to see that that proof can very quickly be generalized to a slightly more general form. I will show you that statement at the end and sort of point to how you could fix the proof. And I'll actually post a full corrected version of a full, not corrected, I haven't done anything yet, a full version of the most generic form of the proof along with the video for this lecture. Okay. So let's look at this claim. So if f is continuous on the closed interval AB, then f is uniformly continuous on the closed interval AB. So again, it allows you to take this sort of local property of continuity. It allows you to take a specialized form of set, the closed interval AB, and it allows you to say, well, if you have a function that has this local property and you have a set that has this specific form, then you can make this more global claim about the function, which is that it's uniformly continuous on this set. All right, let's sketch out the proof of this. All right, so our goal is to show that f is uniformly continuous on the closed interval AB. So we're going to need an epsilon, right? So let epsilon greater than 0 be given. All right. Now our goal is going to be that we need to find some delta greater than 0 such that for any x and y in E, when x and y are within delta of one another, then f of x minus f of y are within epsilon of one another. Okay. We're going to spend a little time working on we're going to build up to how we're going to construct that delta. So this is not going to be a case where I'm just going to write choose delta equal to blank and then fill in the blank. We're going to have to do quite a bit of work to get to explaining how we choose that delta. Okay. So let's start. What do I know about my function? My assumption is going to be that my function is continuous on AB. So since f is continuous on AB, sorry, markers are drying up. So since f is continuous on AB, for each point C in AB, there exists a delta sub C greater than 0, such that for all x in AB, with x minus c less than delta c, we have f of x minus f of c less than. Now I can make this as small as I want, and for reasons that will become apparent later, I don't just want this less than epsilon, I want to make it less than epsilon over 2, right? So what I'm doing here is I'm saying, okay, great. My assumption is that my function f is continuous. That on this interval, that means it's continuous at every point. So for every point C in this closed interval AB, I can choose a delta. Now that delta is going to depend on what C value I'm at. But I can choose a delta sub C such that anytime I have an x value in my interval that's within delta C of x, or sorry, within delta C of C, then f of x minus f of c must be as small as I'd like. And in this case, I want to make that less than epsilon over 2. All right. So now what I'm going to do is I'm going to create an open cover of the interval AB. Okay. So for each C in my interval AB, we're going to consider the open interval I sub C, which is going to be C minus delta C over 2, comma, C plus delta C over 2. Okay. So what I'm going to do is I'm going to go at each point C, and I'm going to create a little interval. Now notice I'm not allowing myself to go the full delta C distance from C. I'm only going half that distance. Okay. But at each, what I'm going to do is at each point C, I'm going to put a little interval of width delta C. Okay. So it's width delta C, so in each direction I can go delta C over 2. Okay. This collection, so if I take all of these intervals for every C value, if I take the collection U of all the I sub C's for all C and AB, this is an open cover of AB. Oops. Now, why is this an open cover of AB, right? Every point C lies in I sub C, right? If you take any particular point, it's the center of one of these intervals. So it lies in one of these intervals. It may lie in many of them, but it lies in at least one of them. So every point in AB is in at least one of these intervals. So it's a cover of this. It's an open cover because each of these I sub C's is an open interval, right? Okay. So this forms an open cover. Now, here is where we're going to first see, compactness probably does have something to do with this, right? Because I have an open cover. I'm on the closed, it's an open cover of the closed interval AB, which is compact. So I should be able to find a finite subcover. Okay. So since AB is compact, it's a closed and bounded interval. So there exists, so I'm going to say it this way, there exists finitely many points So what I'm going to do is, right, I'm covering these first by taking intervals that are centered at every C value, right? I only need finitely many of these. So I'm going to take those points and call them C sub I. There's some finite collection of points. Those are going to be the center of the intervals that I want to keep, such that so my such that my closed interval AB is basically, I just want to say this closed interval AB is contained in the union of the I sub C sub i's for I going from 1 to n. Right? So all I'm saying here is that this is now a finite subcover of the closed interval AB. Okay. And notice we could also express this, right, as we could go back and express these in their interval form. So this is I is equal to 1 to n of, this would be C sub I minus delta C sub I over 2, comma, C sub I plus delta C sub I over 2. So one of the reasons I want to write it this way is I want to emphasize a point now. So let's go back. We had this open cover. It was formed by taking these intervals centered at each point C in my closed interval AB. That formed an open cover of AB because AB is compact. There exists a finite subcover. I'm going to describe that finite subcover by looking at the finite number of centers of these intervals that are left. Okay. And to each of those points that are left in the finite subcover, each of those, the finite number of centers that are left, there's a delta value, a delta C sub I associated to that. So what I want to do now is I'm going to erase what we've written so far because I need more room, but also so we can draw a picture to help illustrate exactly what we're doing here. And maybe to help make this a bit easier, I'm going to invoke a little bit of cleaner here to help us out a bit. And with so many things, mathematical and otherwise, this seems to make things worse before making it better. Yeah, maybe that's also some sort of commentary on where we are in the status of this proof right now, right? It seems seems a little rough right now, but hopefully we're on the downside of what we need to prove. There we go. All right. All right. So now we are going to choose our delta. Right? Remember we said let epsilon greater than 0 be given. We needed eventually to find a delta. So now we're going to find that delta. So now we're going to choose delta to be the minimum of, so all those delta CIs that you have left. Oh, I've run up into the text here. So we're going to choose delta to be the minimum over I between 1 and n of delta C sub I over 2. Okay. So again, back to our picture. So here in the domain, I had my closed interval AB. Okay. And the first thing I did is I went and at every point, I figured out, okay, from continuity, what is what's sort of the delta value where if I'm within delta of this point, I can make sure my function values are within epsilon over 2 of each other. And then I actually cut that interval in half. But in any case, I sort of came up with this little interval width. And I did that at every point. So I covered it up at every point. But then I realized that that forms an open cover. I can take a finite subcover. So at the end, then I come back, like here's a C1, here's my C2, right? Maybe I had a C3 here. There's C3, and it had some delta value. Okay, and then maybe a C4 right here. Maybe it had a pretty large delta value. I don't know, something like that. Okay, so again, associated to, say, this point, right, there was some this distance here would have been delta C4 over 2, but there's some delta value here associated with this point. There's a different delta value associated here with this point, and a different delta value here associated with this point. So what we're doing is we're taking each of those and we're forming this minimum here. Okay. Now there are only finitely many of these, right? Because I've passed to my finite subcover, so there are only finitely many of these. So each of these things is strictly greater than 0. And if I take the minimum of a finite number of things, each of which is strictly greater than 0, that's also strictly greater than 0. All right. All right. Now I sort of have everything set up to do the rest of my proof. Okay. So now remember, my goal is I want to show now I've got an arbitrary epsilon floating out there. And I want to show that if I take two different x values that are within delta of each other, then f of x minus f of y has to be, in absolute values, has to be less than epsilon. All right, so let's take x and y. This was like my x1 and x2, but I'm going to call them x and y now. So let x and y be in AB such that x minus y is less than my delta, which I've defined up here. Okay. Now, what I'm going to do, sort of big picture, the first thing I'm going to do is I'm going to show that x and y have to lie in one of those little subintervals of your finite subcover. They have to lie in one together. Okay. Now, it's possible that they one or both of them lie in multiple pieces of the subcover, but I want to show that if I pick x and y within delta of each other, then x and y have to lie in the same one. There's one subinterval that they are both in. Okay. So to see that, so since the closed interval AB is covered by the finite subcover, well, then if I take my x value has to lie in one of those intervals, right? There exists some I between 1 and n such that x is in I sub ci, right? So any point you pick in AB, right, it's got to lie in one of these intervals that form your finite subcover. All right. Now what I want to do then is I know x has to be in one. Now I want to show that y has to be in the same one. Okay. So what does it mean for x to be in here? It means then that, so if you remember the form of this interval, right, was like ci minus delta ci over 2. This is a case where we start writing so small with all these sub-indexes that it's a little hard to read, comma, like ci plus delta c sub I over 2. Okay, so I'm going to erase this in a second. What I want to emphasize is because of the way this is defined, this means that the distance between x and ci has to be strictly less than delta c sub I over 2. So then that's what I want to say. So then x minus c sub I is less than delta ci over 2. So that just follows from the definition of these intervals. So now I want to show that y is also close to this c sub I by the triangle inequality. Okay, let's look at, I look at y minus c sub I. Well, I could rewrite that as y minus x plus x minus c sub I. So notice here, all I'm doing is adding and subtracting x in here. I'm not changing the value. But now I can apply the triangle inequality. And now I know that y minus x, by assumption, that's less than delta. And delta is the minimum of all these things. So it's certainly, this is less than or equal to delta c sub I over 2. And this value is strictly less than delta c sub I over 2. So since we have, sorry, let me make a slight correction. This actually, we're not showing that y is in this interval, okay? But what we're doing is we're actually showing that y, even though it's not in the subinterval that's centered here, because y, again, all we can say is that it's within delta c sub I, this subinterval had the furthest distance was delta c sub I over 2. So we're not saying it's in the same subinterval necessarily, but what we're saying is it can't be too far away. And in fact, it's still going to be close enough that my continuity condition holds, okay? So since so I'm going to start with the x minus ci. So since this is strictly less than delta ci over 2, which is certainly less than delta ci, then by the continuity of the function at ci, then f of x minus f of ci must be less than, remember we defined those deltas so that that was less than epsilon over 2. And since y minus c sub I is less than delta c sub I, we can again invoke continuity at ci. Then we have that f of y minus f of ci is less than epsilon over 2. All right. And now here's sort of the, or sorry, it's less than, that's not epsilon, that should be epsilon over 2. And now finally, well, then what does that tell us? Then if I look at, I think maybe this is deserving of a new color here, okay, to conclude. So then if I look at f of x minus f of y, this is, I can add and subtract ci. Actually, to make this a little cleaner, let's look at f of y minus f of x. Just make it, doesn't really make a difference, but so if I add and subtract ci, f of ci, now I can again triangle inequality. So by the triangle inequality, I'm going to finish here without having to erase. This will be less than or equal to f of y minus f of ci plus f of ci minus f of x. But now, if I look at this is less than epsilon over 2. This difference, okay, those are just flipped, but they're inside absolute value, so they're the same. It's less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that concludes our proof, right? So let's sort of review this briefly, right? So from the very beginning, we first went through and defined, we sort of wrote out what does it mean for the function to be continuous at each point. And we used that continuity at each point to define this open cover of my interval AB. I used the fact that the interval AB was compact to pass to a finite subcover. I use that finite subcover and those finite deltas, those finite number of deltas to define my overall delta for this problem. Then I showed that if I take two points x and y in my closed interval AB that are within delta of each other, then x and y must both be within delta, some delta c sub I of one of the c sub i's, right? I don't know which one, but essentially they both have to be within delta of one of those centers of my finite subcover. And then invoking the continuity of the function at that point c sub I, I'm able to eventually show that f of x minus f of y has to be less than epsilon. Now, if we think back to sort of what we were first talking about, I proved this on the closed interval AB. I never used anything about this being an interval. The only thing I really used about this was the fact that this closed interval was compact, right? So it stands to reason that I ought to be able to modify this proof to work for any compact subset of R. And in fact, if you go back into this proof and replace every occurrence of the closed interval AB with just a generic compact set E, the proof will work entirely identically, okay? In fact, it's actually a little bit easier because you can end up, I tend to just use the AIs. Instead of using CI for all the center points, I use AI. I don't like using A when we're using the closed interval AB because that sounds like it should be endpoints or something. So I actually think it slightly simplifies the notation of the proof a bit, although that's totally a personal preference. But you can redo the proof very easily for compact subsets of R. And so what I've posted along with this video then is just a written up proof of just that. It'll read nearly identically, although I've added some of the words I said, I've actually added to the write-up of that proof. But I have proven this more general theorem that if F is continuous on a compact set E, which is a subset of R, then F is uniformly continuous on E as well. You can actually generalize this much further. So you can generalize this to a number of other settings, but at least for our purposes, given that how similar the proof is, I thought it was worth at least stating and proving that to sort of, it doesn't make a lot of difference in the difficulty of the proof, so we might as well state the slightly more general version. So what we've seen today is this new notion of uniform continuity. But as we think back about both continuity and uniform continuity, in some ways, what they were doing were classifying functions by how their outputs change based on how their inputs change. So if you think about continuity at a point, right, a function is continuous at a point if you can essentially control the output sizes, right, the difference in outputs by limiting your input values, right, the range of inputs. Now, essentially, all the definition of continuity does is control that enough to prevent your function from jumping, okay? Uniform continuity does something similar, although it works on a whole interval. And now what we might think about is sort of further drilling down on this notion to say, well, could I actually quantify how those output values are changing with respect to input values? Okay. That, of course, is going to lead us directly into the notion of differentiation and differentiability. Okay, so starting in the next video, we will explore the definition of the derivative and begin to look at different properties of differentiable functions.